So in the previous video, we took a look at how we can use u-Substitution in order to evaluate different indefinite integrals. And in today's video, we're going to look at how we can actually extend this notion for evaluating definite integrals. And so here we have the definite integral from e to the pi over 2 to e to the pi of a negative sign of ln of x over x dx. And so kind of the first thing that we have to do here is we kind of just have to think about how we can use u-Substitution in order to just evaluate the indefinite integral. We don't really have to care about these bounds of integration for the moment. Let's just think about what the antiderivative of this expression over here is. And so let's go ahead and do that. So we have this natural log of x that's being input into the negative sign function. And then we have this 1 over x on the outside. And we know that natural log of x's derivative is just 1 over x. And so what we can do is we can let u be equal to the natural log of x, and then du is equal to 1 over x dx, right? We just took the derivative, multiply both sides by dx. And then with that in mind, we have over here the natural log of x over inside of this negative sign function. We have this 1 over x dx. And so what we can just do is write this as the integral from e to the pi over 2 to e to the pi of negative sign of u, right? Because we said u is equal to the natural log of x, and then we have 1 over x dx. That's just going to become du. And so now we have a much simpler integral. So we just used a little bit of u-Substitution. And so now we just have to go ahead and evaluate this. So we know that the antiderivative of negative sign of u du is equal to cosine of u. And we're evaluating that from e to the pi over 2 to e to the pi. Now, there's a couple of things we can do here. We can't just go ahead and say, okay, this is going to be equal to cosine of e to the pi minus cosine of e to the pi over 2. This will not work. And the reason why we can't do this is because if we wanted to, then we're essentially assuming over here that we're saying u is equal to e to the pi. U is equal to e to the pi over 2. But in reality, we aren't. Here we're saying that x is equal to e to the pi over 2. That x is equal to e to the pi. Because if we go back to the original integral, here we're kind of implicitly stating, when we're taking this integral over here, we have, the integral from e to the pi over 2 to e to the pi of this expression dx, then we're implicitly stating, because of this dx, we're implicitly stating that x is equal to e to the pi over 2, that x is equal to e to the pi. And when we make this u-Substitution, we're still saying that x is equal to e to the pi over 2, that x is equal to e to the pi. And so we can't automatically just switch up when we take the antiderivative and say that u is equal to e to the pi over 2 and that u is equal to e to the pi. So there's a couple of ways we can approach this. The first thing we can do is we can either just say, okay, this is going to be cosine of, instead of u, we replace u with the natural log of x, right? So we can kind of just back substitute is what we would call it. Just like we would when we want, when we evaluate an indefinite integral and we want to describe it in terms of x instead of u, we kind of just back substitute. And it's the same thing for the definite integrals. And when we do this, then it's actually valid to say that this is we're going to evaluate this from e to the pi over 2 to e to the pi because we back substituted. So now this is in terms of x. We have here x is equal to e to the pi over 2, x is equal to e to the pi, and we have our x back in our antiderivative. Now our antiderivative is in terms of x, not in terms of u, and hence the bounds of integration should be kept in terms of x. So we evaluate this, we get cosine of pi minus cosine of pi over 2. That's just going to be equal to negative 1, if I'm not mistaken, because this is 0, this is negative 1. And so that would be our final answer right over there. And that's the first way we can approach it. And let me actually switch colors now for the second way. So let's take this purple color. Okay, so this is the first way we could do it, is we can kind of back substitute, redescribe it in terms of x. The second way is we can change the bounds of integration and describe them in terms of u. So here we're saying that x is equal to e to the pi over 2, x is equal to e to the pi. If we want to kind of change that to u, we just have to look at the expression for u. So u over here is the natural log of x. We can implicitly write this. I mean, u is really just u of x, right? It's a function of x, and it's, in this case, ln of x. What happens to u when x is equal to e to the pi over 2? So what is u of e to the pi over 2? Well, that's just the natural log of e to the pi over 2, which is just pi over 2. And same thing, what is u? What happens to u when x is equal to e to the pi? Well, that's just going to be equal to pi, right? So essentially now we have our new bounds of integration. Instead of e to the pi over 2, we just have pi over 2. Instead of e to the pi, we just have pi. And so now in this expression over here, this integral that we were initially taking, this one up here, we can go ahead and write this now all in terms of u. We can change the bounds of integration and describe it in terms of u. So now instead of the integral from e to the pi halves to e to the pi, we have the integral from pi over 2 to pi, right? Because this is from u is equal to pi over 2 to u is equal to pi of negative sine of u du. And then we would just evaluate this like we would any other integral. So then we get cosine of u. We're evaluating that from u is equal to pi over 2 to u is equal to pi. And then we ultimately end up with cosine of pi minus cosine of pi over 2 minus cosine of pi over 2. And then that's just going to be equal to negative 1. And so we end up with the same exact answer. But in this particular circumstance, we didn't actually have to back substitute. Instead, what we did is we just changed the bounds of integration. So we kept our antiderivative in terms of u, but we had to change the bounds of integration and make them in terms of u as well. So essentially, this is kind of the main outcome here, is when you're taking an antiderivative or a definite integral and you're using u-substitution, then you have to make sure that the bounds of integration, that the variable that the bounds of integration are written in terms of actually matches the variable that the antiderivative is written in terms of. So here we wrote our antiderivative in terms of x, right? So we kept it in terms of x. Then we have to write the bounds of integration in terms of x as well. Over here we kept the bounds of expression in terms of u, right? We didn't want to back substitute. We just kept it cosine of u. Then we also have to make sure that the bounds of integration are in terms of u. And so I hope that this makes sense. Essentially, just be very careful whenever you're using u-substitution for definite integrals, because you want to make sure that the bounds of integration actually line up with the variable of integration. And so in the next video, we're going to go over a couple more examples just to really set this idea. But I hope that this is not too confusing, and I hope I didn't go too fast here. So definitely be careful when you're using u-substitution for definite integrals.